Welcome to Molecular Polarity. In the last video, we talked about polar bonds and what makes a bond polar. Now in this lesson, we're going to look at the effect of polar bonds on the molecule that they're a part of. To look at the effect of this, we're going to look at a couple of examples. So first, let's consider water. Water has a Lewis structure that looks like this, as we're all probably very familiar with by now. We also know, based on electronegativities, we could find out quite easily that the bonds between the hydrogen and the oxygen are polar. And in fact, the hydrogens have a partial positive charge, and the oxygen has a partial negative charge. Bond polarity basically tells us about the sharing of electrons within that bond, the distribution of electrons within that bond. So basically it's saying that the electrons in these bonds are going to be closer to the oxygen than they are to the hydrogens. Now this has an effect on the molecule as a whole. What it does is it makes the oxygen part of the molecule significantly more negative than the hydrogen part of the molecule. In fact, we could draw a line through this molecule and make two sides of the molecule, one side being positive and one side being negative. We can also see this in the charged cloud model that's shown over here, where the red atom in the middle is the oxygen, and this sort of red shaded area is a region of higher electron probability, the more negative region, whereas these bluer regions by the hydrogens are the positive regions. Because one side of the molecule, the oxygen in this case, is more negative and one side is more positive, and the molecule essentially has two poles. We call it a polar molecule. It has one side that's more negative and one side that's more positive. So water represents a case where we have a polar molecule with polar bonds forming it. In the next case, we're going to see something a little bit different. So next, we're going to look at carbon tetrachloride. Carbon tetrachloride has a central carbon surrounded by 4 chlorine atoms, all covalently bound. And these are polar bonds as well. Okay? The chlorines are all slightly negative. So I can write in my partial negatives, partial negative, partial negative, partial negative, partial negative. And the central carbon, therefore, is going to be the partial positive. Now this is a molecule that's made up of polar bonds. However, you'll notice that it's symmetrical in its arrangement. The top bond is basically completely opposite in polarity to the bottom bond. And the direction of polarity on the left bond is entirely opposite the direction of polarity on the right bond. So basically the bonds that are opposite each other are canceling each other out in terms of polarity. This perfect symmetry results in what we call a nonpolar molecule. And this particular nonpolar molecule is made up with all polar bonds. So this is a case of a nonpolar molecule that's made up entirely of polar bonds. The last case is basically any molecule that has nonpolar bonds in it. Okay, I don't need to break this up into further categories. Any molecule made up entirely of nonpolar bonds is going to be a nonpolar molecule. Okay? It has to be a nonpolar molecule. So we don't really need to get into much more detail with that. That's just an important thing to point out. So to wrap up, the one thing that's incredibly important, the sort of key idea behind this whole thing, is that a polar molecule is a molecule that does not have symmetry in its charges. Or to put that another way, a perfectly symmetrical molecule will be nonpolar as a molecule, no matter what the bond types are. When determining the polarity of a molecule, it's important to keep two things in mind. One, the geometry of the molecule. Okay, that's that idea of symmetry. A symmetrical molecule is going to be nonpolar. If a molecule has a lack of symmetry in the way the charges are distributed, or any kind of partial negative, partial positive regions, it's going to be a polar molecule. So let's put symmetry there as a way of remembering what we're looking for. And symmetry equals nonpolar for the molecule type. The second thing to keep in mind is any lone pair electrons or non-bonding electrons. they usually contribute a strong negative charge to that region of space that they occupy, and that can create a polar molecule pretty easily, like we would see in the ammonia molecule, which is NH3. Looks like this. Okay. In this molecule, the lone pair contributes strongly to a negative region around the nitrogen atom, and that creates the polarity in the molecule. That wraps up our lesson on molecular polarity. Any questions you have from this lesson, make sure you write them down in your notes and bring them with you to class.